this is APAB Calculus. We're doing 1.3, and we're going to talk about two little things that sort of occur at the end of the section today. We're going to talk about the Squeeze Theorem, which is on page 67 in the textbook, and also two limits that for now you should just memorize, although in the long run I'm going to show you how to find them when we learn L'Hopital's, when we do 8.1, which we will actually do in chapter 2 in such a confusing world that we live in. So anyway, let's talk about the Squeeze Theorem first. So I copied verbatim the really mathy definition of the Squeeze Theorem. THM is a math abbreviation for theorem, in case I haven't said that before. That's an acceptable abbreviation. The Squeeze Theorem, remember that things in math are named either after a person or something that is descriptive, right? Like slope-intercept is named after using a slope and an intercept in the equation, right? So the Squeeze Theorem is not named after somebody named Squeeze. Mr. or Mrs. Squeeze would be a great villain in a movie. The Squeeze Theorem is so named because what we're talking about here is we're talking about two functions that are squeezing another function. So we're going to talk about the Squeeze Theorem first, then I'm going to walk you through a couple questions about it, and I'll show you a visual of what it looks like. I'll be perfectly honest, in 20-some years of doing calculus, I don't use the Squeeze Theorem very often. The most likely way you are going to see this is where you are asked, like you're given a visual that is applying the Squeeze Theorem and you're asked if you know what theorem it is. It's very unlikely that you're going to have to apply this out of nowhere, but I just want to walk you through it. So I'm going to see, we'll see if my markers hold up, and if they do, I'm going to give you some color coding. So I'm going to use purple for the H function, and orange for the F function if they hold up, and I'll use this like aqua or whatever for the G function, okay? So basically the idea is that we have three functions, H and F and G, and in these three functions, H is on the bottom, it's lower than F, which is in the middle, which is lower than G. Now, it says lower, less than or equal to, but just picture that H is the shortest, and then F is slightly taller, right? The Y values are higher, and then G is slightly higher. On some open interval containing some point C, except it doesn't actually have to contain C itself, and we'll talk about that in a sec. Now, when I'm in a classroom demonstrating this, I do it with me and two other people under normal circumstances. So what I'm going to try to do over here is give you a visual that is sort of a bad recreation of what it would look like if I were going to draw this diagram in a classroom with me and some other people. Sorry, the marker lids are just really stubborn about staying on. Okay, so here's what it would look like if we were in my classroom, right? So the front of my classroom, we have like this board, right? And then somewhere, right, we have a doorway, somewhere that we're just going to call the X value of C. Right, we have the door to leave the classroom, and outside the classroom there's a hallway, right? So there's a hall out here, and this is room 209. So in here we're in room 209, and out here we're in a hallway, right? And there's this doorway right here, okay, that I'm going to say occurs at x equals c. So here's the idea. So in this room, right, the G function is doing a thing, right? And the G function is always the physically highest of the three. So the G function's doing a thing. Right, okay, so that's my G of x, right, up and down, up and down. And the H function is always the lowest of the functions, so maybe my H function is way down here, but it also has to go through the door, right, H of x, okay. And then my F function, right, is usually me, so I usually pick one student to be the G function on top and one student to be the H function. And my F function might do a lot of crazy stuff. It might even get to the point where it touches one of the other functions. But what it's going to have to do is it's forced to stay between them because H is below F, which is below G. So my F of x function has to stay between them. So now, because this is a door, and I was trying to draw it like these were actual people, right? Like my G function, my F function, my H function are people. I gave us some space. But what it would look like on an actual graph is that if H and G are walking to exactly the same Y value, right? If that Y value they're walking to, so let me make this a little bit more accurate. Let's say that they're walking to the point where they're literally touching at this Y value that we're going to call L, okay? So my H and my G are walking to exactly the same Y value, which we're going to call, let's just give me a Y-axis right here for a sec. So we're going to say that this Y value right here is Y equals some number L, right? So if G and H are both walking to L as x approaches C, right? So the G function has to be approaching this Y value of L on both sides, right? Double-sided limit equals it has to be equal, so both sides they're approaching this value of L. and my h is approaching that same L, because G and H are essentially on either side of F, what's happening is F is squeezed in between, and F also has to be approaching that same Y value. So where you see this applicable is usually you're given some ugly G function, and you pick some pretty easy, ugly F function. You pick a pretty easy G and a pretty easy H function, and you show that at this point you're looking for, at x equals c, or in this, like, it could be x equals 5, or x equals 0, or x equals infinity, or whatever. You show that these two functions have the same value at that point, and you show that this function's always on top and this function's always on the bottom, and that this ugly function is stuck between them, then what you've proven is that those two functions are going to squeeze together and force the other function to go to the same y value at x equals c. So when I do this with the kids, what ends up happening, again, this is in a pre-coronavirus era when we could actually be like within 6 feet of each other, is that we end up running all over the room, and then when we get to the door, we all awkwardly squeeze together, right? So Squeeze Theorem, right? It's called the Squeeze Theorem because you have a top function and a bottom function that are squeezing together and forcing the other function to go to the same y value. Now, does that mean that you're going to have to apply this regularly? No. Does it mean that this is how some of the limits that you might end up memorizing or that you might learn, is that this is where they come from? Yeah, totally. But for our purposes, really, you just need to recognize what the Squeeze Theorem is and how it works. So we are going to walk through one example of the Squeeze Theorem, which is going to be, I believe, our E6, if I'm leaving off at the correct spot. And then we'll come back to these two limits. But I'm going to erase this spot. Again, just to be clear, the reason you would use the Squeeze Theorem is because if you were handed a limit where none of the algebraic stuff that we already did worked, like you couldn't factor, you couldn't FOIL or distribute, you couldn't get one common fraction and cancel something, you couldn't rationalize, you've got nothing, then you might have to do this. But again, I don't expect that you're going to see a problem like that. I think at most you would be expected to spot that this is the Squeeze Theorem. And that's it. Okay, so let's walk through one Squeeze Theorem problem. Now, I have to do a little bit of a cheater thing that is not entirely fair, because in order to do the Squeeze Theorem example that I'm going to pick, I need to give you a little bit of information. So just a little bit of like relevant info that is not technically from this section. Anytime you put a finite number on top of something infinite, positive or negative, you get a 0. The idea being, it doesn't matter if you have $1 million. If you divide them infinitely, all of those infinite people would get $0, right? So anytime you take a finite number, no matter how big, if you put a finite number on top of something infinite, you will get a 0. So the reason that that's worth noting is, let's say A is a finite non-zero number. The limit as x approaches either a positive or negative infinity of a over x is going to be 0. Because if you put a finite number that's non-zero on top of an infinite number, you're going to get 0. Okay? So it's just worth noting. It's going to come up a lot in math later for us, but unfortunately to do this one particular example I have of the Squeeze Theorem, you're going to have to just accept that that's true. All right, so what we're going to do for our Squeeze Theorem example is we are going to find the limit as x approaches infinity of sine of x over x. Now that's not the same as this limit that I have at the bottom here, because this one's approaching 0 and this one's approaching infinity. So you can't just plug infinities in because sine of infinity is not actually a thing. Sine oscillates between 1 and -1 forever, which we're going to talk about. We talked about oscillating limits in 1.2. And if you plug infinity on the bottom, you're definitely going to get an infinite number. Now, there's always a clever person on this video that makes the clever argument that if sine is in fact, and actually it doesn't even have to be a finite non-zero number, I lied, it can just be a finite number. Somebody clever is going to make the argument that this has to be a number between -1 and 1 inclusive. So it's got to be a tiny finite number, even if we don't know which finite number it is. And if you put an infinity on the bottom, well, hey, that's a finite number over something infinite, and the answer is 0. And it does turn out that that intuition is correct, and the answer is going to be 0. But we're going to use this one as a Squeeze Theorem example. So the trick here is that what we know about sine is that sine is always greater than or equal to -1 and less than or equal to 1. right? That's if you picture what you know about the unit circle, the biggest sign of x can ever get is 1, the smallest it can ever get is -1. So what that means is that I could write that -1 over x is less than or equal to the sine of x over x is less than or equal to 1 over x. Well, I know that this guy and this guy are both 0 as x approaches infinity, right? I know the limit as x approaches infinity of -1 over x is 0, based on this thing I told you about putting a finite number on top of an infinity. I know that the limit as x approaches infinity of 1 over x is also 0. Again, same argument, finite number over x. And since I know that this is between them, right, this has to be in the middle, then that must mean that the limit as x approaches infinity of sine x over x is squeezed between these two things at 0, or at infinity, which means that it also approaches 0. Again, I think some of us could have intuitively figured that out. What I've personally found with squeeze theorem problems is that my gut intuition is almost always right. So if I were just asked to evaluate this limit, my gut intuition would have told me that it was a 0. And then the squeeze theorem just validates that intuition. So most of the time you're not going to be asked to apply the squeeze theorem. They're just going to want you to figure out how what the answer to the limit would be. And even that, like, honestly, I don't expect that you would see this on an AP exam. So realistically, you just need to be able to spot that it's a squeeze theorem. All right, so let's instead move on and talk about now 2 other limits that I'm going to suggest that for right now you memorize. Long term, you don't have to have these 2 limits memorized. At the end of chapter 2, we're going to skip and do a quick time jump to 8.1 and do L'Hopital's. And when we learn about L'Hopital's, you're going to learn how to find both of these limits. So if in about a month or a month and a half or whatever it is, you choose to completely forget and not have these memorized, you're going to have a way to figure them out, and that's fine. But for right now, you don't have a way to figure them out, so you just need to make a note card and commit them to memory. When I say make a note card, what I mean is make this one side of the note card and make the other side of the note card, right? Make this one side of a note card and make the 0 the other side so that you can quiz yourself. We're going to have a lot of note cards in this class because there are a lot of things that you have to memorize. You're going to have to memorize a lot of derivative rules, you're going to have to memorize a lot of antiderivative rules, and you're going to have to memorize a bunch of other things, especially once you get to BC Calc. But again, you want to have some of this information readily available because knowledge is stuff that you've memorized, and cleverness is the ability to apply it in smart ways under pressure, and that's something I can't teach you, right? So what you can teach yourself to do is memorize the stuff that's important, and then the only way to get better at being clever with it is to practice, practice, practice. Okay, so these 2 limits, the limit as x approaches 0 of sine x over x is 1. Now, if you tried to just plug in, you would get sine of 0 on top of 0, which sine of 0 is a 0, so you get 0 over 0, and so you might say, oh, hey, Hogan, you totally told me that if I get 0 over 0, there's a way to simplify it, and I can clean this up and figure out, you know, the value of this thing. And I did tell you that, and it's true, but you don't know enough information to simplify this yet. So unfortunately, since you don't know enough information to simplify this yet, you just have to take my word for it and know that if you were able to, it would end up netting you a 1. Similarly here, 1 minus cosine of 0 would be 1 minus 1, so it's a 0 on top of another 0. Remember, 0 over 0 is never the answer, just like it's an indeterminate form. And again, you just don't know enough to figure this out yet. You have to take my word for the fact that it's a 0. So we're going to use those 2 basic limits, and using those, we're going to flip to another example. All right. I know I had one for you. There it is. All right. So I'm going to actually borrow one from your book. So we're going to go ahead, and this is actually our example 7, but it's going to be example 9 on page 66 of the book. So for example 7, our example 7, right, is going to be example 9 on page 66, okay? So we are going to evaluate the limit as x approaches 0 of tangent x over x, right? Now you can try and plug in because it never hurts to plug in, but if you plug in, you would get tangent of 0 over 0, which is totally a 0 over a 0, and that's never the answer, right? So we've established that in the other 0 over 0 problems. That's never, ever, ever the answer. As a side note, if you were having trouble with where I got tangent of 0 in my head, you want to get pretty comfortable with the unit circle, right? So tangent is the y on top of the x at the unit circle, right? So the tangent of 0 would be 0 over 1, which is how I got the tangent of 0 is 0. You do want to be familiar with the unit circle. It is going to come up regularly. So anyway, so I get 0 over 0, which is never the answer. Now, I can't simplify this using all of those other things we learned, because unfortunately, none of those other things we learned had anything to do with trig. What I can do is try and write this as some version of these guys that I memorized. So I'm going to remember that there is a trig ID that tells me that the tangent, I'm just going to use theta, tangent of theta is sine over cosine. The reason I picked theta is because I wanted to make it clear that this was a random trig identity and it wasn't me plugging into here. So tangent of x should be sine x over cosine x. So I'm going to rewrite this as the limit as x approaches 0 of a sine x on top of a cosine x, all on top of an x, which is really over 1, right? Everybody's secretly a fraction. So that means that this is the limit as x approaches 0 of a sine x over cosine x times a 1 over x, right? Because when I divide by a fraction, I flip and multiply by the reciprocal. Well, I'm going to put this in a slightly different order. I'm going to make this the limit as x approaches 0 of sine x over x times a 1 over cosine x. Now, an interesting property of limits is that if I have a limit of a product like this, I can split it apart and make it two separate limits. I can say, hey, it's this limit times this limit. Well, this limit is one of the two that I just told you to memorize. So we already know what that is. And this one, I'm okay to plug in, because if I plug in, I get a cosine of 0 on the bottom, and cosine of 0 is 1, because again, on the unit circle, at an angle of 0 radians, the cosine is a 1. So I get that this thing is a 1 because I memorized it, and that this thing is a 1 over 1 because that's 1 over cosine of 1. So I end up getting that the whole answer is a 1. So the trick here is that what we hadn't done yet in 1.3 is we had not simplified things that involve trig functions, right? And so that's another, so when you're simplifying limits that involve trig functions, for right now, and again, long term, I'm going to give you another way to do this problem that I think is a lot easier, but I'm not going to give you that way to do it until we get to chapter 2 because you just don't know enough stuff yet, which is sort of the nature of math, right? You don't always know everything you need to know. All right, so let's walk through another example. So we'll do a P7 that's similar to this. Right, so P7. Let's do well, that one seems a little easy. Let's do the limit as x approaches 0 of a sine x times a 1 minus cosine x over a 2x squared. Okay, so you're going to try and figure out this limit. If you want to pause me, now is the time to do it. So when I first look at this, my first thought is that if I split the x squared on the bottom into two separate x's, right, if I write the bottom instead of the way it's written as a 2 and an x and an x, I can actually split this up into two of the limits that I've memorized, and also an annoying little 1/2. Now, I didn't bother to do the plug-in really quick, but if you had plugged in, sine of 0 is 0 times 1 minus 0 all over a 2 times 0, which is definitely 0 over 0, which, remember, is never the answer. So I can split this up essentially into three different pieces: a 1/2, a sine x over x, and a 1 minus cosine x over x. Well, this was one of the ones we memorized. It's a 1. This was another one we memorized. It's a 0. And there's nowhere to plug in here. This guy's just a 1/2. So essentially, you get 1/2 times 1 times 0, which is a 0. And that's your answer to the limit. All right, let's do one more of these as an example, which we'll actually do the one that's listed as example 10 on page 66, and then I'll give you one more practice problem. And then after we do that, we'll call it a wrap on 1.3. All right, so we're going to call this E8, but it is actually example 10 in the book on page 66, okay? So we're going to do the limit as x approaches 0 of sine of 4x on top of an x. Now what's tricky here is that the pattern that we were given was sine of something on top of the something, right? So the tricky issue here, right, is that if, sorry, computer zonked for a sec, okay? So remember that the pattern you were actually given, and I'm going to erase P7 so I have a little bit of room to play with here. The pattern that you were actually given, and I'm not going to use x's here, I'm going to use something else. Let's use the limit as theta approaches 0. It was sine of theta on top of theta. Well, this 4x is the thing inside the sign, and I can't change that, right? Like there's a 4x, and this is not a 4x, right? But here's what I do know. I do know that as x approaches 0, 4x also has to approach 0, right? Because if your number is approaching 0, multiplying that number by 4 also makes it approach 0, right? So I know that if I were able to make the bottom a 4x, I could fit this pattern, where I have sine of something over that same thing. I can't change the fact that there's a 4x inside here. So what I'm going to do is I'm going to take my entire limit. I'm going to take this limit as x approaches 0 of sine of 4x over x, and I'm going to times the whole thing by a 4 over 4, which I'm allowed to do because all I'm doing is multiplying by 1. So I think that's going to give me the limit as x approaches 0 of a 4 times this sine of 4x over a 4x. Well, this is the pattern I was looking for, right? So I think that that gives me the limit, and I can remember as we discussed up here, if x is approaching 0, then 4 times x is also approaching 0. So the limit as 4x approaches 0 of a 4 times the limit as 4x approaches 0 of this pattern. Well, this pattern is something we memorized. It's a 1. And this limit is just a 4 because there's nowhere to plug in. This number is always a 4, right? It's not 4x, it's not 4 over something, it's just a 4. So I'm going to get that this is 4 times 1, which is a 4. So while I have that example 8 there, I'm going to give you a similar one. Let's do, so for P8, I'm going to have you do the limit as x approaches 0 of sine of x over 5x. Okay, now if you want to pause me, this is a great time to pause me. So the trick here is that actually the x is the thing inside the sign, right? So I don't have to worry about the fact that there's a number in front of that. I could just make this a 1/5 times a sine x over x, right? Because that's a 1 over a 5, right? There's no number inside the sign. So this is the limit as x approaches 0 of 1/5 times the limit as x approaches 0 of a sine x over x. Well, that's a 1/5 because there's nowhere to plug in. It's just always a 1/5. And we've established that this is one of those memorized limits that's a 1, so my answer is a 1/5. Okay? Now, one thing that I should touch base on really quickly, because I didn't explicitly address this, limits function in a really boring way like completely regular numbers, right? So let's do a quick review of properties of limits, okay? And I think it's really just properties of numbers, right? So properties of limits, because limits are really intuitive. These are intuitive because they work like numbers. They really do. So if I wanted the limit as x approaches some c of an f of x plus or minus a g of x, if I were adding two things together, I could just add the two separate limits. I could just find the limit for f plus or minus the limit for g. And I said add a second ago, but it's a plus or minus. So if it were a minus, it'd be a minus. If I were multiplying two limits, and we've already seen this, as x approaches c, f of x times g of x, right? I could just multiply the two limits separately. Right? And then division's a little tricky. So if I have a limit as x approaches c of f of x divided by g of x, I can do exactly what I'm doing, which is just make it two limits. The limit as x approaches c of f of x divided by the limit as x approaches c of g of x. But there's a caveat. The limit as x approaches c of g of x cannot equal 0, right? Whenever you see one of these caveats, you have to ask yourself why. And most of the time, the answer is because you can't divide by 0. There's one other thing. Let's call k a constant, right? So k is some constant. The limit as x approaches c of k times a function, you can just yank that k out in front. And that actually makes a lot of sense if you think about it, because essentially, if you look up here, I could just treat it as two separate values, the limit as x approaches c of k, and then the limit as x approaches c of the function. Well, it is worth noting that anytime you have a limit as x approaches some value of a constant, it's just the constant because there's nowhere to plug in, okay? So that's a quick review of property of limits, and again, I hadn't expressly stated them, I've just kind of been using them, so that's kind of the idea, okay?